In this video, we're going to take a look at our other method for finding the volume of a solid of revolution. And this method is called the cylindrical shells. So keep that in mind that we're going to be looking at cylinders. So the idea is that we're going to take our region, just like we have before. We've got this region underneath our curve from A to B and going to the x-axis. So we're going to take this region and we're going to spin it and rotate it about the y-axis, and then it's going to create this solid shape, so a cylinder that's kind of got a dimple in the top. So the way that we're going to find the volume of this, instead of slicing it, we're going to take a look at slicing up the region itself like this into strips. So the idea is we're up here in this region and we're going to cut it into strips. And the picture that we have down below here is one of those strips, and then we take and rotate one of those strips around the y-axis and it creates a cylinder. It creates basically that cylinder that doesn't have a top or a bottom. And then the idea is that we'll take these other strips that we have cut up here in our original function and we'll spin them around and create these nesting cylinders that we've got. So it's the idea here that we're kind of taking like two biscuit cutters that are pretty close in diameter and cutting out this cylinder, and then we build up these cylinders and it will make our full solid um, solid that we want to make. And so the idea is that we'll make this delta x, or this dx, I guess that's going to be delta x at this point. The delta x, we're going to want to make that smaller and smaller so that we get more and more of these cylinders. And so our area that, or our volume that we're approximating with our cylinders, is going to get closer and closer to the actual volume of that. So what we have to figure out is, okay, well, how are we going to get the volume of each of these cylinders? Just like, how did we get the volume of each of those discs? We looked at the area of the face of that and then times its thickness. Well, same idea here. We're going to look at its thickness. The thickness of each of these cylinders is going to be our delta x. So if you look back to how we made that cylinder, we took that little strip that has a width of delta x and we spun it around. So our width is delta x, that's our thickness down here. And then our cylinder, if we take and cut it open right here on the side and unfurl it, which is what we're doing in this picture, that makes a rectangle. And the length of our rectangle is going to be this radius. Well, it's going to be the circumference of the top. That's why we need the radius. So this length is the same as that circumference. So we get 2 pi times that radius. And that radius, where we're going to get that, if we go back up to our picture, the radius is from here at the y-axis out to our strip there. And so that's x. And then we need the height, so how tall this cylinder is. And again, our height up here, we look at where we got that strip, that's our f of x, that's the output. So we've got the volume is equal to the length times the width times that thickness. It's kind of like the height of these cylinders. Although I guess this guy's the height. So maybe it's the width and thickness that are the same. So let's rewrite that. That is the height. There we go. So the length, that's the 2 pi times our radius, which is x. Right? Again, that's our radius. And then the height of this is that function value. And then the thickness is going to be that delta x. So we're going to take each of these cylinders, so our total volume is going to be the sum from I equals 1 to n of 2 pi x sub I star and then f of x sub I star, sort of where we pick to have that radius, and that then gives us the height, times our delta x. And of course, what we're going to do is take the limit here as n goes to infinity. because we want more and more of those cylinders. And this is going to lead us to the integral from a to b of 2 pi x f of x dx. So that's how we're going to find our volume using these cylinders. And again, it is a volume because we've got, three quantities multiplied by each other. So thinking unit wise, we've got x, we've got f of x and dx because that's our thickness. And so here's our, our little kind of summary box from our textbook that using this method of cylindrical shells, we get 2 pi times x times f of x. So what's going to be nice about this is that we don't have to square that function. So we may end up with some slightly easier integrals because of this. So let's take a quick look at a volume that we make that we're going to rotate around the y-axis and that will be useful to use with cylindrical shells. So here is our graph, and let's reflect this. Our region that we're looking at is here from 1 to 2 above the x-axis and under that function 1 over x. And so if we reflect this around, we're going to get, here's our reflected shape, and we're spinning it around the y-axis. And we're going to get something that looks like this. So we've seen shapes that kind of look like this before. It's back behind there. It is kind of a lampshade sort of shape, but it's got that cylinder taking out of it in the middle there. Now, what's a little different than our disk method is in our disk method, we looked at the axis that we were spinning around because that gave us what our variable is going to be. Here, our variable is actually opposite the axis we're spinning around because when we go and make a cylinder, it's again like we're taking a cookie cutter and cutting down into our figure, and here is our cylinder. And so its thickness, kind of put it, the thickness kind of that way, it's sort of hard to draw the thickness, but the thickness there, what we're chopping up into pieces is the x-axis. So our variable here is x, even though we're spinning around the y-axis. So this is a way for us to find the volume of functions that are defined in terms of x that are spun around the y-axis, so the opposite axis. And our integral is that we're going to look at this from 1 to 2. Those are our limits of integration. That's the part of the x-axis we're looking at from here, 1 to 2. That's what we spun around. And then our function that we're taking the integral of is going to be 2 pi x. And that's that part. That's our radius of the top of our cylinders. And then times 1 over x, because that gives us the height of our cylinders. And then times dx, because that's the thickness of our cylinders. So this actually is pretty easy because x times 1 over x cancels out, gives us just 2 pi. And we get 2 pi x from 1 to 2. So 2 pi times 2 minus 2 pi times 1. So we're going to get, let's see, 4 pi minus 2 pi? Yep, so 2 pi.